Okay, our next speaker is Negin Rahimi. Negin is a research assistant professor here at the College of Information and Computer Sciences at UMass Amherst. Before she came to UMass, she worked at the Chinese University of Hong Kong. She received her bachelor's and PhD in computer science at the University of Tehran. Her latest work investigates explanations of deep learning to rank models. So trying to understand what the models are actually doing for information retrieval and search results. Today, she's going to talk about information seeking and learning. Sound good? And she's going to speak as loudly as she can. I do want to warn the people in the back that because of the microphone system locally, we can hear everything you say very well. So, but if you can't hear Negin, please raise your hand so we know we can try to do something about it.
Okay.
Thank you, Negin.
I'm trying to hear as much as I can. So thanks, James, for the introduction. I'm going to continue on the topic that Razieh talked about and see how information systems can help us, can help our learning process. So is it all good for the back? Awesome. Okay. So as Razieh mentioned, when we want to learn, meaning that we want to gain new knowledge about the topic, we do search, and searching for information plays a big role in our learning process. And then there are different learning objectives. So according to that, there could be different search tasks for different learning objectives. Now, it's not only us that we try to learn things. There are also many machines and neural models that also try to learn knowledge to perform different tasks. So we learn by searching for information, and machines and neural models can also learn by searching for information as we do. So there are similarities and differences between learning by humans and machines. Accordingly, there are similarities and differences between search tasks that are performed by humans and by machines to get knowledge and get new knowledge and learn things. So now that we know that search is an integral part of human learning and can be a part of machine learning, there could be two different research questions about this. One is how we can optimize search models, not only for relevance of information, but also for learning process. The other question is that when we have a search models, we get search results from this model. How can we optimally represent these search results to the learner so that we can help them in their learning process? Because we know that when users, or machines in general, learners get the search results, they need to investigate the search results. They need to compare different items in the search results so that they can learn. So in this talk, I want to focus on the second question. So we have a set of search results. I want to see how we can represent these search results to learners to help them in interpreting search results and learning. So to answer that question, we want to first see what are the search tasks that have learning objectives. So based on different learning objectives, we can have different search tasks, but it's been observed that one of the main search tasks for learning is exploratory search. What is exploratory search is that when users have questions about with open-ended answers. So there's no definite unique answer to the question. There could be multiple answers to the question. And usually they have questions about multifaceted information needs. And learners are trying to learn, so they are not familiar with the information space relevant to their questions. They are not certain about their objectives and their goals that they want to achieve. And all of this make, learners to formulate queries for search systems that are not very well formulated. And an example of a question that is kind of exploratory search task is that when we ask, how can we search results be presented so that we can assist learners interpret them? Okay, so given these properties of exploratory search, I want to focus on these two properties. We have a large multifaceted information space in the result set, and we want to present that to the user. So one way that we can help users to interpret this set of results or large information space for the information need is to help them with providing facets explicitly. So that's where our work on aspect-oriented explanation of search results can be helpful for this task. So we have a query, we get a set of search results, we want to explain each document that's part of the search results and constitute the information space by query aspect that it covers. So here's an example that we have the query of Madrid. We want to say that there are different aspects about this question. We want to know about culture, history, popular sports in this in that country or things like that. So for each document, we get this set of aspects that are covered by that document. Now, how we can generate this explanation? There are two different ways to generate this kind of explanations to help users. One setting is that we generate these explanations in a black box setting. So we have a search results, we don't know or we don't use the models that has been used to generate such results. So we try to explain this set of documents or information space just by using the textual information that we have here. So another way is intrinsic explanations, where explanations can be generated from the model itself. So when we want to generate explanations from the model itself, we need to design search models in a way that they are more interpretable so that we can use that property to generate explanation intrinsically. So because the focus of this talk is about presenting search results, and this setting needs development of search models, I'm going to focus on the first setting and see how we can generate aspects, these explanations in a black box setting. So again, the problem is we have a query, a set of search results, we want to explain them. One way is to get one document at a time, try to come up with its explanation, and at the end, aggregate all the explanations that we have for different documents in the search results, and then get that as the explanation of the information space. But it would be more optimal if we can explain the entire information space as a whole, so that we can consider document interactions in the set that we have. That way we can see if a query aspect or a facet of the question is stated, described differently in different documents, how documents cover the same thing or different things. That would help users when they get to different documents, they can better compare them or faster compare them to see what are their differences, what are their similarities, and they learn better, or at least they get a roadmap for their exploration. Now, when we want to explain all of this as a whole, then given the constraints of the transformer-based encoder, we cannot pass the entire information space as the input of the transformer-based models. So, how can we address that challenge? So we cannot pass everything at the token level to the transformer-based models. It's true. So we aggregate the representation to come up with the coarse-grained document representation. So that's what is mostly done. But in our approach, we design that iteratively. So we make fine-grained token representation, aggregate that to get coarse-grained representation. Based on that, we encode document interaction, update those things, and then again, those interaction-based encodings impact fine-grained token representation. So this model has been trained without human-labeled data and successfully generate different granularity of aspects for different queries. That some of them can be very general, some of them specific. And given the time, I just show you that it improved the strong baseline at the time, but no more description on the results here. Now, this aspect-based moving toward learnings of machines, these aspect-based explanations can also be given to the machines, but there are other questions, research questions about machine learning when they are augmented with search results too. So one of the things is that when humans search for information, they get results that a mixture of relevant and non-relevant information. And as a human, we can process the things and come up with what is related to our information. It's frustrating, but we can handle it. Now, when machines learn for information, how can they come up with the quality of search results when they want to use those search results? Okay, so given the differences between human and machine is that when we want to help the machines to come up with the quality of search results, we have better flexibility because for users, we want the information provided to be readable in a limited budget so that the users are not overloaded, but we don't have such constraints for models. So one of the examples here is that we retrieve search results by ranking them based on a score, and then providing a score to user is not likely to help them, but we can provide such scores to models. Now we consider that in the task of language modeling, when everything is frozen, and we want to see how search results can be used by a frozen language model. So the language model wants to complete this input, search for information, and then the retrieved results are this, where two of them are not relevant, one of them is relevant. So we show that among many other multiple analysis that is in the work, we show that if we only use the retrieval score for the machines, and then based on that, adjust how search results are integrated in the target task, we can improve the perplexity. And then the work that I described here are done with this group of researchers. And now I can take questions. Now I think I cut it more than I needed.
Anybody have any questions?
So you mentioned there's a limitation for the max token size for the language model. Can you like step more into like how do you concatenate like the whole document information into a single embedding?
So yeah, so we just like mostly use, we pass document tokens to get the representation, and instead of just one time aggregating this token level representation to get document representation, we also update the document representation as another input, to self-attention models. When these document representation are updated based on document interaction and similarities between documents and differences between documents, we use those coarse-grained representation to again update this token level representation. So I have a slide that how this is done by changing the architecture of transformers by adding a global layer. So each time that we do the local layer, we have a global layer that updates document representation, and then this global layer, then inside this global layer, we have broadcast and add operation that updates fine-grained token representation of documents. So we need document representation so that, we can generate fluent and coherent descriptions out of that, those detailed representation.
Thank you.
I wonder if you could say something about the what actually happens, because I think I kind of missed that. What happens when you suddenly have non-relevant information injected into the, because that's what you were talking about toward the end, right? So what is the effect, or do you know yet what the effect on these aspect-based explanations will be if the aspects are coming both from documents that happen to be relevant and some non-relevant documents that any search engine is likely to return?
Okay, so we address that in the intrinsic models, intrinsic explanations. And then the point was like when we measure the similarity of the documents to come up with the aspect descriptions with self-attention thing, we based on the weight assigned to documents, we ended up getting like low weights assigned to non-relevant information, so that we had a better way to handle those. So but I don't have a slide about that to show more details of the model, that how this weighting helped us to reduce the impact of non-relevant information in coming up with the aspects.
Questions? Thank you, Megan.